This is an oxygen dissociation curve for haemoglobin. We've looked at this last lesson. It's a sigmoidal shape because for the first oxygen molecule to bind to the haemoglobin molecule is more difficult. Once it has bound and the haemoglobin is 25% saturated, then the next two oxygen molecules bind more easily until we get to about 75% saturated, and then it's a bit harder for the final oxygen molecule to bind to the one free heme group, just due to the probability being small that an oxygen molecule will collide with the free heme group. So that explains the S-shaped curve. What we can also say here is that at high partial pressures of oxygen, 12, 11, we've got a high percentage saturation of haemoglobin with oxygen. And at low partial pressures, we've got a low percentage saturation. Now we need to start talking about the affinity of haemoglobin. The affinity is how easily oxygen can bind to haemoglobin. Okay? If it can bind at low partial pressures of oxygen, it therefore has a high affinity. Normally you would need quite a high partial pressure of oxygen to get a high percentage saturation of haemoglobin. If it can unload oxygen at high partial pressures of oxygen, so therefore at high partial pressures is actually not very saturated, then it is a low affinity. So what dictates this affinity? It is actually the structure of the haemoglobin itself. The order of amino acids within the polypeptides will determine the position of the disulfide bridges, the ionic bonds, holding the polypeptide in its tertiary structure. The tertiary structure is how it's folded around the heme group, and that will determine how easily it is for the oxygen to get to the heme group to bind. Okay, so its tertiary structure, its shape affects its affinity. And we've said down here that when the first oxygen molecule binds to the first heme group, it causes a change in the shape of the haemoglobin, meaning it's much more easy for the next two oxygen molecules to bind. Right, today we're going to look at two different haemoglobins. There's different haemoglobins because there's different alleles for haemoglobin polypeptides, different alleles for haemoglobin polypeptides because they've arisen by chance through mutation, and certain alleles have been selected for because they confer an advantage. So I am going to draw on two more oxygen dissociation curves. Okay, so we're going to say that this one is a mouse dissociation curve, and this one is an elephant dissociation curve. Now one has moved to the right, shifted the curve to the right. The other one has shifted to the left. Okay, let's just have a look in detail at these curves. So at a 5 kilopascals partial pressure of oxygen, if we just follow this up, the mouse haemoglobin is about 10% saturated. Okay, if we have a look how saturated the human haemoglobin is, it's about 55% saturated. Obviously we're estimating these. And if we follow that up to the elephant, it's about 90% saturated. So at the same partial pressures of oxygen, The mouse haemoglobin is only 10% saturated, meaning that it's given up 90% of the oxygen that it was carrying. The human haemoglobin is 55% saturated, meaning it's given up 45% of the oxygen it was carrying. And the elephant haemoglobin is 90% saturated. It's only given up 10% of its oxygen. If it's still holding on to its oxygen, like the elephant haemoglobin, it's still bound to it, it's closely associated with it, it's still got an attraction to it, we say that it's got a high affinity. So if you move the curve to the left, it's got a high affinity. The mouse at the same partial pressures, so using the same partial pressure to compare the three types of haemoglobin, the mouse is only 10% saturated, so it's given up 90%, so it's not got a high affinity at all. In fact, it's unloaded it much more easily. So if you unload oxygen at a fairly high partial pressure, it's got a low affinity. So the mouse has a low affinity. So if we shift the curve to the right, we have a low affinity. If we shift the curve to the left, we have a high affinity. And we can compare the affinities by taking a value of a partial pressure of oxygen and comparing the different percentage saturation of the haemoglobins with oxygen. Okay, why has this happened? So I said that it's because they've got different polypeptides that make up their haemoglobin molecules. Those polypeptides are coded for by different alleles. Those alleles have arisen through mutation, and they've been selected for over thousands, hundreds of thousands, millions of years even, to be prevalent. Lots of low affinity haemoglobin in the mouse and high affinity haemoglobin in the elephant. Okay, why is that an advantage for a mouse to have low affinity? Well, what do we know about mice? This is what you need to do when you come to application questions. Mice are small, they're warm-blooded, as are elephants and humans. They've got a very large surface area to volume ratio. They therefore lose a lot of heat, and in order to maintain their body temperature, they will have a very high metabolic rate, a high rate of respiration, which generates heat to maintain their body temperature. So they have a high demand for oxygen in their tissues, so they need a low affinity haemoglobin that's going to give up the oxygen much more readily. So we need to say mouse equals large surface area to volume ratio equals a lot of heat loss, high rate of respiration, increased demand for oxygen to maintain body temperature. Okay. Now, once we know about high and low affinity, we can apply this to anyone. Most of the examples you'll have is to do with size of the organism, surface area to volume ratio and heat loss, therefore a higher demand for respiration. But we could go back the other way, and this could be here we could have a lugworm. A lugworm lives in little burrows in the sand, and they actually extract oxygen from the seawater. When this tide comes in, their little burrow fills with seawater, it's got a high oxygen concentration, life is good. But as they start to use, the tide goes out and all they've got is that water that's in their little burrow, and they're using up the oxygen from their water, and the oxygen levels are decreasing and it's becoming depleted. So we're having low oxygen concentrations. So at this point, you need a haemoglobin that's still going to be saturated, that will still bind at low partial pressures. So here at 2 partial pressures, it's already 30% saturated, whereas the humans is only 5% saturated. So we can go the other way. The final example I wanted to show you was fetal, this is a fetus, fetal haemoglobin, it has a higher affinity than the mother's haemoglobin because it needs to be able to attract the oxygen from the mother's haemoglobin in order to bind. Otherwise the oxygen would stay bound to the mother's haemoglobin. Okay.